Good morning, everyone. It gives me great pleasure to introduce Philip Wadler as an invited speaker at ZuriHac 2020. For most of you, Philip requires no introduction. Not only has he made significant contributions to functional programming and the design of Haskell, his contributions can also be seen in other areas of programming language design, such as Java and XQuery. The Zurich Friends of Haskell and the HSR are very grateful to Philip for accepting our invitation to talk at ZuriHac 2020. In case any of you want to ask Philip any questions, please use the #talk-discussion channel on Discord. I will interrupt Philip during the talk for clarification questions and save more general discussion questions for the end of the talk. So take it away, Philip.
Hi, good morning, everybody. We're in this brave new world where I can just roll out of bed and then be speaking to the entire world. But also, so that's an amazingly good thing. But when I'm doing this, the ability for feedback is much limited over what it normally is. So normally I would be looking out over all your smiling faces, maybe taking a photograph of all of you to commemorate how great this is. And instead, here I am in my living room speaking to all of you. Nonetheless, it is live. We do have some occasions for interaction. I see there's a private chat field. There's nothing in it right now. If somebody puts in a smiley or something, that would be wonderful. I should begin with a joke, but there's no point because if you laugh, I can't hear. But that's a joke. So if you enjoyed that joke, you can put a smiley in the chat field. I can get some feedback in that way. Oh, yes, some smileys are entering. Excellent. Old-fashioned smileys. So I'm going to talk to you today about Programming Language Foundations in Agda, a textbook that I wrote. Let me just bring up my opening slide. Come on. Okay, so here we go. So let me talk to you about Programming Language Foundations in Agda. This is a textbook that I wrote with Wen Kaka, and later Jeremy Seek has added a new chapter, which is available now. I'm at the University of Edinburgh. I also work for a cryptocurrency firm called IOHK, and I'm fortunate enough to spend part of my year in Rio de Janeiro, where my partner lives. And Rio de Janeiro is a great place to work on functional programming because, as you can see, the streets are paved with lambdas. Everywhere you go, you can find lambdas in the street. So here's again, there I am. Again, I'm actually used to remote working because, as I say, I'm at the University of Edinburgh. You can actually see Edinburgh up in the corner here. This is a painting Vanda has of Edinburgh Castle. But there I am in mine and Vanda's sitting room in Rio de Janeiro, working on this textbook. So it was all written remotely in her textbook. So we are in a world now where we can do a lot remotely. And recent events have really brought that home to us. But the world's been changing like this for a fair number of years. And for instance, right, we are these days and fly to one location so that we can do have meetings like this one. But when we do that, we put huge amounts of carbon in the atmosphere. So I think there is something to be said for doing that maybe a bit less often and doing things virtually a bit more often. So even though this was thrust upon this is nothing that anybody would choose to do. I think that the opportunities that this is giving us to learn about how to do more things virtually. At my university next year, we're going to be teaching the whole year virtually. And in many ways, that's horrible for the students, right? Normally students should be in one place. They should be able to get together. They should be able to party. They should be able to teach each other in the same room and maybe do other things with each other in the same room. And instead, they're all going to be, there's going to be some hybrid system that's part virtual and partly with people being there. And many people are lamenting this is not the usual experience. And that's absolutely true. And there are a lot of things that are valuable, I think, that will be lost. But I hope we won't lose track of the fact that there's also maybe a lot useful that can be gained. And what I'm doing right now, and what you're doing right now, is exactly part of that. And for instance, learning to interact well in these circumstances will be part of that. So, oh, I'm not going to go through that because you guys know about that. Let me talk to you about the textbook I've written, Programming Language Foundations in Agda. And some of you who know me will know that I'm known for puns. And when I first came up with this title, I thought, I can't possibly use that title. That's not a pun. And then I realized, actually, it is a pun. So the key thing about Agda, so I should explain, right? You guys know about Haskell, I think, many of you. It's a very popular functional programming language, something I was involved with, along with many other people. And then Agda came along a bit later. It was done by a bunch of researchers at Chalmers University. They were familiar with Haskell, and a lot of the design of Agda is strongly influenced by Haskell, and then in other places it differs. So Agda is what's called a dependently typed language. Dependent types are becoming more and more the rage these days. They let you express much more in your type system. They let you express so much that you can rigorously prove something. So I'll show you a little bit about how we can specify just what addition is, and then we can actually prove things like that addition is associative or addition is commutative. And of course, we know all this for addition, but if you're coming up with some new structure, then being able to prove these things is quite valuable. I'll say a little bit about how you can take a mathematical model of programming and turn it into something you can execute because it's being done in a constructive proof theory like Agda. So, sorry, I'm going to pause from time to time because I don't have faces to look at while I'm pausing. I'm just going to pause and think for a moment about what the next thing to say is. If I'm in an audience, I know how to do this and make it look right by looking around the room into all your faces. But here I am all by myself, and all of a sudden my mind goes blank. I just pause for a moment. I think on the camera, that looks horrible. And I apologize for that. That's one of the things I'm going to have to learn how to do properly. So if I do just pause for a moment and go, and look horrible, my apologies for that. I'll try to do this in a sprightly way. So, programming language foundations in Agda. Agda is fantastic. You can do proofs in Agda. What does it mean to describe a proof about language foundations in Agda? It's just code written in Agda. So I had this was my working title for the book, but it wasn't a very interesting working title. I thought, I can't possibly go with that. I need a pun. And then I realized it is a pun. So the pun here is, you can parse this two ways, right? So the obvious way to parse this is it's about the foundations of programming languages in Agda. So programming languages grouped together, and that's foundations in Agda. But what did I just tell you? If we want to learn things about language foundations, if we want to prove things about that's just code. So what we are doing is taking language foundations and programming them in Agda. So there you go. I'm allowed to use this title because it is a pun. And that pun sort of gets to the foundation of what I'm most interested in, which is something called propositions as types, or the Curry-Howard form. Sometimes it's called the Curry-Howard isomorphism. And the whole idea about propositions as types is that every interesting construct in programming, things like records or sum types, also called variant records, and functions, we all know about functions, each of these has a correspondence in logic. So records, the simplest kind of record is a pair with two fields, a first of type A and a second of type B. That's exactly like a conjunction in logic. So a record with an A and a B field is like a proof of A and B. A sum that has either an A field or a B field is like a proof of A or B, and an implication, A implies B, sorry, a function, A from A to B, is an implication from A to B. So that's what this book is about teaching. I assume this is a fourth-year course at Edinburgh. It's written as a textbook. It's freely available online. Let me actually do this. Let me stop sharing for a minute, and then I can wave at you big. But then let me bring up something else. I'll share the screen again. I'll just share the screen and bring it up. And let's go to, let's go to the web. Here we are. And here's the textbook. It's online. Here's the table of contents. Here's some material about where else it's been taught and so on. And let's just zip into the first chapter. And the whole textbook, actually, you can see it's very nicely colored. Each bit that's been colored here is colored because this textbook is an Agda program. And as Agda processes things, it works out, okay, data is a keyword, 0 is, so I'll put it in red, 0 is a constructor, so I'll put it in green, and so on. These are all variable names bound elsewhere, so I'll put them in blue. So this is a declaration of natural numbers in Agda. It's like a data type declaration in Haskell. And what this is telling us is that 0 is a natural number, and successor is a constructor that, given a natural number, returns another natural number. So for example, 3 would be suck of 0. So these bits are in black. This is not executed Agda, which is a shame because it means I can have a typo in there and I won't catch it. But here, if I make a typo, it would be caught when processed as Agda. So this, every bit that's in color, it's wonderful. You know that is correct. And it's a brilliant idea being able to write a textbook online that you can execute. So it's online, it's freely available. That will always be the case because you have to be able to download and execute and modify the code in the textbook for yourself. So it will always be freely available. And this idea of being able to write something which is also code that executes, it's called literate programming. It goes back quite a ways. When I was a student of Don Knuth, in the trying to remember back when, back in 1974, I think it was, he was already telling us about literate programming, which he had invented as a way of writing out the code for the LaTeX processor. Sorry, TeX it was then. LaTeX came along later. Leslie Lamport.
We have a clarification request from the chat. Someone is asking if in the code snippet here, if set is a kind, like in Haskell.
Oh, right. So what's going on here? Yes. So this looks like a type, and then this would be the type of a type, which in Haskell is called a kind. That's a great question, because what's actually going on in Agda, you notice here we use just 1 colon for constructor 0 has type n, and then here we also use 1 colon for type n has kind set. And the reason for that is in a dependently typed language, it's all the same. And that's because you can have values which appear inside types. That's why it's called dependent typing, because types can depend upon values. So it's all one thing, and everything. So types themselves are values. Values themselves are types. It's all one thing. And so the typing relation, 0 has type n, and the kinding relation, n has kind set is all the same thing. So this can just be read N has type set. So that's kind of weird and surprising. And there are difficulties that appear there. It turns out that if type could have type, that you get into difficulties. Because in order for proofs to be consistent, they must correspond to programs that terminate. So what's the one thing we know? We know that there are some programs that don't terminate. What's the other thing we know? That in general, to being able to decide whether a program terminates is not decidable. You cannot have a computer program that you give another computer program and it decides if it terminates. That's because there's a paradox that would arise if you fed a version of that program to itself. You could use that program to decide if it terminates, and if it thinks it terminates, it then chooses not to terminate. You could easily write such a thing. There's no right answer to whether it terminates or not. And that was Turing's proof back in the 1930s that there is no such thing. So the one thing we know is you can't tell if things terminate. But it turns out in type theory, this is wrong. If you have a well-typed program, it's guaranteed to terminate. And the type system doesn't allow set to have type set. Instead, you have a hierarchy of these things where set 0 has type set 1, set 1 has type set 2, and so on. It gets a wee bit tricky, but in return for this, fortunately in the book, there's only one place where I need to mention set 0 and set 1. So most of the time we can just work with set. And sorry, while I pause to think what I need to say next. And everything is guaranteed to terminate. So we'll see where that crops up a little bit later. And you guys are very used to induction, but this is the point where I get to, inductive types, which is what this form is. We call them algebraic types often in Haskell. But notice, right, what suck is, it says, given an n, I'll give you back another n. Well, wait a minute, how do you know what you're given if that's an n? Right, so we know that, well, 0 is an n, that's our base case. And then from that, I can do suck of 0, which gives me 1, and then suck of 1, which gives me 2, and suck of 2, which gives me 3, and so on. And this way I can get every number there is. And the fact that this is done recursively, we seem to be defining n in terms of n, is perfectly sensible. Everybody who's familiar with algebraic types in Haskell will be very familiar with that idea. But it's an amazing idea, because how many natural numbers are there? Let's see, let's count them. 0, 1, 2, 3. If I tried to count all of them, you might get bored. If I tried to get all of them, I would exceed my time bound for this talk. And in fact, even if ZuriHac was very generous and they gave me 2 or 3 hours or 1,000 years or 1,000,000 years or 1,000,000,000 years to give this talk, and I tried to count all the natural numbers, I wouldn't finish, because there are really a lot of natural numbers. So the name we have for this is, we say it's infinite. And you're all used to the idea of infinity. But here's the amazing thing. 1, 2, 3 lines, and I've defined all of the infinite number of natural numbers. How cool is that? So we can define an infinite number of things in a very small space. And as you'll see, we can prove things about an infinite number of things in a very small space. So I'll move on and show you a little bit more of the textbook. I said I was going to show you defining and proving things. But just before I do that, I want to make a point. I got this great clarification question. If I say something that you don't understand, please put it in the chat and put clarification in front of it. And then I hope our wonderful moderators at ZuriHac will pick that up and tell me what the question is and I'll try to answer it right away. So please ask clarification questions if I say something you don't understand. If there's something you want to discuss or something deeper you want to ask, that's more of a discussion question. Please leave that for the end. But clarification questions, we're live here. We should take advantage of that. And please ask them right away, because I apologize if I say something that you've not understood. That's my fault for not explaining well enough. Please help me do my job by asking clarification questions. Okay, so now we've got the natural numbers. What can we do with them? Well, we can do things like we can add. Let's skip down a bit. Here we go. Here's the definition of addition. Now, when I was young, I learned this from an addition table, right? And I memorized for the first 9 digits what the sums were. So like 7 plus 8 is 15. How could I work that out so quickly? Because I memorized it. And you, when you were young, all memorized it too. So you memorized the table, the addition table for the numbers from 0 to 9, added with a number from 0 to 9. That's 100 special cases. And then you've learned the rules for adding 2-digit numbers or 3-digit numbers or 4-digit numbers in terms of all these. And there are quite a few rules to learn. And again, once you've learned those rules, it's great, because you could write those rules out in a page or two. And that's amazing then, because in that page or two, you've described how to add every number that ever could possibly exist, all infinity of them. So again, in just a small finite space, right, this 10 by 10 table and some rules for dealing with larger numbers, we can capture all of infinity. But here's something even cooler still. We can capture all of that in just 3 lines. So here we go. Plus takes a natural and a natural and gives us back a natural. And how's that defined? 0 plus n is equal to n. The successor of m plus n, what we're going to do is we'll take m and add it to n, and then take the successor of that. And you notice all of this, we're just rearranging where the parentheses appear. So it seems very natural. So 0 plus anything is the other thing. Successor of m plus anything is that. And again, wait a minute. I'm defining plus in terms of plus. How could that possibly be right? But it works. And here's an example. Let's show that 2 plus 3 is 5. When we write 2 plus 3, that's just shorthand for 2 is the successor of the successor of 0. 3 is the successor of the successor of the successor of 0. And then we need to match this equation. So when we're doing here, successor of 0 is the first thing, and 3 is the second thing. Successor of 0. And so which equation matches? Is 0 the same as successor of 0? No. Is suc m, could that match successor of 0? Yes, if m is successor of 0. So this is 2, m becomes bound to 1, n is bound to 3. And then to compute 2 plus 3, it says compute 1 plus 3, and then take the successor. And we go around, we do the same thing again. Is 1 plus 3, is 1 the same as 0? No. Does 1 match successor of m? Yes, if m is 0. So now we say 1 plus 3 is the same as the successor of 0 plus 3. And then we go back again. 0 plus 3, does 0 match 0? Oh yeah, it does. So 0 plus 3 is 3. And here, I've written that all out in Agda, so it's checked. There's no possibility for an error. 2 plus 3 is successor of 0 plus suc 0. And then here we've got 1 plus 3 with the successor of that. And here we've got 0 plus 3 with the successor of that. So ultimately, it ends up being the successor of the successor of the 5. So that's all there is to it, and Agda checks it for us. And there's one thing in Agda which I really like compared to Haskell, which is its way of dealing with infix. So you notice that here we've written underbar plus underbar, and these underbars stand for the place where the arguments go. So here it tells me that if I write m plus n, that's just shorthand for writing underbar plus underbar applied to m and n. And the nice thing here, so Haskell has nice notation for infix, but this goes to multifix. So I can do things like if underbar, then underbar, else underbar, and so on. It's used very heavily in the book. Another thing that's used heavily in the book is you notice these ends here look funny, but they're not in ASCII. But in Unicode, there are an awful lot of characters, including these fat ends. So I use Unicode heavily in the book. And so it can end up looking a lot like what you'd normally write on a blackboard as mathematics, but now we can type it into the computer and get Agda to check it for us. Just going to stop sharing for a minute. And that means I think you can see my face large for a moment. I'll just pause here for a second and just ask, are there any other clarification questions at this point?
I think everyone is following along splendidly. Thank you.
Okay, great. Let's go back to sharing the screen then. Right. This always takes a couple of minutes to do, and it's a bit clunky, and I apologize for that. Okay, somebody asked me to do hide on this, so I will do that. And let's go back. So now we know how to do addition, but we can do even more than that. Oh, let me go on to the next chapter, actually. And now we can do proof by induction. So a typical thing you might want to prove is that an operator is associative. So m plus n plus p, whichever way we put the parentheses. So we can first add m and n together and then add p, or take m and add it to n and p, and that will be the same thing. You're very used to that, right? That seems completely obvious. But in fact, it's kind of amazing that no matter which way we group things, it works out the same. Another example is commutativity. M plus n is the same as n plus m. So whichever way around you do it, it's fine. And there are more interesting things like distributivity. If you take m plus n and multiply it by p, that's the same as m times p plus n times p. So these are all things we might want to prove. An example, right, here's associativity. Here's an example of associativity checked by Agda for us. So if we do 3 plus 4 plus 5, that's the same as 3 plus 4 plus 5. Well, duh. But it's not as obvious as it thinks, right? 3 plus 4 is 7. So here we've got 7 plus 5. 4 plus 5 is 9. So here we've got 3 plus 9. When you look at it that way, wait, 7 plus 5 will be the same as 3 plus 9? Well, yeah, it is. They're both 12. But why is that? Can we prove that? Well, yeah, we can prove it. Again, there are an infinite number of cases here, right? There are an infinite number of choices for m, another infinite for n, another infinite for 3. So that's 3 times infinity cases to deal with. But we can deal with that all, again, not in 3 lines this time, but there you go. If it's on 1 page. And that's how many lines? 1, 2, 3, 4, 5, 6, 7, 8, 9. 20 lines. So in a score of lines, we can prove for all the infinite number of cases that this will be true. And how do we do that? Well, we do it by case analysis, what's called induction. So there are 2 possible cases, right? The first number might be 0, or it might be successor of n. If it's 0, well, 0 plus n, by the rules we gave before, is the same as n. But the other way around would have to be 0 plus n plus p. But again, 0 plus n plus p is n plus p. So 0 plus n plus p, so 0 plus n simplifies to n. So this all simplifies to n plus p. This all simplifies to n plus p. Okay. By the way, you're learning here an important thing about how you read equational proofs. This is the left-hand side we want. This is the right-hand side we want. We simplify this going down. We simplify this going up, and then they meet in the middle. So we'll do the same thing here. There's one other case to look at, which is successor of m and n and p, and successor of m plus n plus p, parenthesized the other way. So we've got parenthesized each way. And we simplify. Remember the rule said that the successor of m plus n is the successor of m plus n. I have to pronounce the parentheses in my voice. Let's see if I can get this right. The successor of m plus n is the same as the successor of m plus n. That was one of the rules we had. And we just keep the plus p on the end there. And then now we've got the successor of m plus n, and we add that to p. And again, that will be m plus n plus p added to successor. Going up, we've got successor of m plus n plus p. So that becomes the successor of m plus n plus p. So I've gone through this very quickly. It's much easier if we kept going back and looking at the definition of addition and seeing how they matched exactly. You can go back and do that in the textbook if you want to. But I'll just point out that all of this is colored properly. And what that means is that Agda has checked all of this. So I cannot be making a mistake here. If I were, Agda would be pointing it out. So finally, now we've got this and this. Oh, but they're not the same. This one has the parentheses to the left. This one has them to the right. Oh, if only I had a theorem that told me that addition was associative. Ah, that's what I'm trying to prove. I can't use what I'm trying to prove it, can I? That would be bad. That would be like using a function to define itself. I would get into an infinite vicious circle. But no, right? We already saw that the recursive definition is fine. It's fine to define recursion on bigger numbers in terms of recursion on smaller numbers. That's because it always gets smaller and smaller and smaller, and eventually we hit 0, which is the base case. We're doing the exact same thing here. We're going to prove associativity on suc m plus n plus p in terms of associativity on m, which is smaller than n and p. So this will terminate, right? The trick is just you must call the function on something smaller. So when we do that to define addition, it's called a recursive definition. When we do it here, it's called proof by induction. And now you can see that recursion, which you're probably very familiar with, and induction, which you may be less familiar with, are two sides of the same coin. They are.
There is one clarification request from the chat.
Yep, great.
That is whether or not ASOC here is a reserved keyword, or if you can just pick any name that you would like.
Okay, good clarification question. So everything that's in blue is just a name that I've defined. So this is the definition of a plus ASOC. I can pick any name I want. And oh yeah, it's sort of weird, right? Because this name has a symbol plus and a symbol dash, and then some letters, right? We're used to names normally being just letters, maybe with some numbers at the end, but it has to begin with a letter. But here I've begun with plus. So Agda is a little bit different. Names can be any sequence whatsoever, but then how would you tell when one name ended and another name began? You must have spaces between them. So there are a couple of things that are built-in keywords that Agda knows about, like parentheses. But apart from that, sort of everything is just an infix operator defined as normal, and there must be spaces between the different bits. So spaces become really important, but it means you're very flexible in what names you can choose. So here the name plus a soc is a function that has this type. For all m, n, and p of type n, it returns a proof that m plus n plus p is equal to m plus n plus p. Notice this technically is a type. This is a quantifier, just like, right, for all type A, for all type B, we can take a list of A and zip it with a list of B and get a list of AB pairs, for instance. This is the same kind of quantification. But then this is actually a type. And notice the type has values, m, n, and p in it, and operations on values like plus in it. But this equality here is actually a type. So this is a type that's inhabited if this is equal to this, and there are no values of the type, so it's false if this is not equal to this. So any type that has a term of that type corresponds to a proposition that you can prove. So terms have types, but propositions have proofs. So type has terms that belong to that type, that have that type. Proposition has a proof of that proposition, and these are the same relation. And that's the idea of propositions as types, which could just as well have been called proofs as terms, or proofs as programs, to be more alliterative. Yes?
Sorry, another clarification question. The Kong there is then also a user-defined term.
Sorry, which is the user-defined term? Kong.
The Kong,
yes.
Kong suck.
Right, so Kong actually shows up later. So notice that here we've only proved that m plus n, right, this proves that m plus n plus p is the same as m plus n plus p, but we need to write a suck in front of that, right? We need that suck of m plus n plus p is the same as suck of m plus n. So this is the proof that m plus n plus p associates. And this says, okay, since those two things are equal, if you wrote a suck in front of them, they're still equal. And Kong is short for congruence, which says if you've got two equal things and you apply the same function to both of them, they're still equal. So yes, Kong is defined. In fact, I think it used to be that if you clicked on this, it would take you to the definition, but there was a bug in the program, so I'm not sure it works. Let's try it. Yes, here's the actual definition of Kong in the standard library for Agda. And in fact, in the next chapter of in chapter 4 of the book, you get the definition of Kong, and it's finally explained to you. So there's a little bit of stuff that's used before it's defined, but all the definitions can just be found in the Agda standard library. So yeah, that's a great question. Nope, Kong is not built in. You can just define it. Equality is not built in. You can just define it. Chapter 4 shows you how to do it. There's very little indeed that needs to be built in to Agda. Okay, that was great. So that was what I want to show you in the textbook. You now know how to prove arithmetic is associative. So let me, oops. How do I turn off screen sharing? Oh, I can go here. Stop screen sharing. Okay, hi. There's me big again for a moment. And I'll just pause again and ask if there are any other questions.
We have some questions for at the end, but in terms of clarification, I think we're all good for now. Thank you.
Okay, great. Thanks, everybody. If I've said something that was confusing to you, the whole textbook is available online. It's at plfa.inf.ed.act.uc. I'll put that at the end of the talk as well. And it's freely available. You're welcome to look at it to resolve any questions you have. If you're really confused about something, you can also drop me an email. I hope I won't get 400 emails, but maybe I'll get 1 or 2 friendly emails. Let me go back to sharing the screen again. Okay, and let's now go back to the presentation. So I'm going to skip over all that. I'm going to see, what do I want to do here? So, programming language theory is all about something called lambda calculus. I'm not going to show you that definition in detail, but here's the first part of the definition of type lambda calculus. And as you can see, if I use a small font, it fits on 1 page. So I can explain things like how you define lambda terms, the typing rules for lambda terms. It's not on this page, but you can also give the reduction rules for lambda terms. And it's all fairly compact. And in fact, in the book, I do it twice. Once I do it the normal way, where we write things like, where's an example here? Lambda x arrow n has type A to B. And it can all be done neatly. It takes 2 chapters of the book. But then there's another way of doing these things called the Brunnen indexes. And now I just write that lambda gives you a term whose type is A to B. So now the typing rules are actually built in to the syntax. So this way of writing things is called extrinsic. I first define syntax for terms and types, and then I give typing rules relating terms to types in a given context. Here, I happen to give the syntax for types, but then the typing rules are actually built in to the syntax of terms, and notion of a context and what the type is built in. So I say, here is a term whose type is, here's a term which in context gamma has type A. Here's a term which in context gamma has type A to B. Its context, its component is a body, which in context gamma extended by A has type B. That's gone by very quickly. Don't worry if you're confused by that. You can read the book to get more details. But here's the interesting thing. This way of doing things takes 2 chapters of the book, and the book has to be in small print. This takes 1 chapter of the book, and then you can see as a result, there's less on the page, so it can be in larger print. In fact, when I compare, what I did, using named variables and extrinsic typing, it was 451 lines of code, omitting examples. With de Bruijn indices and inherent typing, it's only 275 lines. If you take the ratios, you see 451 over 275 is 1.6, roughly. 275 over 451 is 0.6, roughly. And if you know your maths, you know if you have 2 things that, if you take the inverse, right, we just split these around, they differ by exactly 1. That's something called the golden ratio, which shows up a lot in mathematics. And you can see this is more compact by about the golden ratio. So it's really much more compact. So I'd always thought before, these are 2 different ways of doing things. This is good for explaining things to people. This is good for computers. But no, this is actually really good for explaining things because it's so much more compact. Now notice that the types in this case, I just gave an ordinary syntax for them because the types don't themselves have types, but in dependent typing, they do. So an interesting question is, how do you do all this in dependent typing? Do you get this same savings? And the answer is, I think so. But even though we've been doing this for many years now, right? Type theory goes back to the mid-70s. This notion goes back of using extrinsic versus intrinsic types. Well, De Bruijn indices, again, go back to the 70s when De Bruijn invented them. The first paper on extrinsic versus intrinsic is back at the turn of the millennium, so 20 years ago now. We still don't know a good way of doing dependent types inherently typed. When we learn how to do it, things will become better by the golden ratio, but we haven't learned it yet. It's a very interesting open question. If somebody wants to look at that, I think it's one of the most interesting things to look at. And it's not deep mathematics. It's how do we make the coding of this work? So that's a fun, interesting, open problem. The other thing that I want to mention is we do proofs of things. So there's a proof that we want to prove. There's a thing we want to prove called, nope, I haven't done this here. There are two properties that you want to prove when you have a type system. I've not written them out here. That's because we saw them before, right? Here they are. They're called progress and preservation. So progress says, if a term is well typed, then one of two things happens. You can take a step, it gives a reduction step, or it's a value. So here I've just explained a disjunction. Disjunction is just a declaration like this. How can you get progress on M? Well, either M reduces to N for some N, or M is a value. So it's just a disjunction. This is true or this is true. And the progress theorem tells us that if M is well typed, then there is progress on M. And here's the proof done in intrinsic form. And you can see it fits very easily on a page. This is an inductive proof that people would learn to do. I won't go through the proof, but you can see it's fairly compact. This is in color, which means Agda has checked it for us. That's one theorem. It says, if a term is well typed, then either it takes a reduction step or it's a value, which means you're done reducing. There's another proof, which I've not shown here, called preservation, which says if a term is well typed and it takes a reduction step, so if M steps to N and M has type A, then N also has type A. So reduction preserves types. And the interesting thing about this deduction is when I prove it, I always tell you which is the case. So as part of the proof, I have to tell you, is it done or does it take a step? And if it takes a step, I have to tell you exactly which step it takes. And that means when I've done this proof, I actually get for free an evaluator. This is great. This is amazing. If you know about constructive logic, once you've seen this, it's completely obvious. This is the whole point of constructive logic, is when you prove something, it gives you a way of getting out of that proof information about the thing you've proved. So it's not surprising that proving this gives me an evaluator, but it's only obvious once you've seen it. And here I quote from various papers which talk about things like, to test the semantics, one must actually use it to evaluate programs. Functional big step semantics can do this out of the box. You specify something by writing an evaluator, as can some small step approaches. And then it quotes these two things, which are specialized systems, the K system by Grigori Rosso and others, and RedX, part of the PLT scheme. Well, it used to be called PLT scheme, now it's called Racket, by Robbie Findler and others. And both of these are specialized built-in systems that animate your reduction rules for you. And at the time I was working on this, I was very familiar with the K system. And excuse me, I was very familiar with the K system. And I had what I called K envy. I wanted to be able to reduce things. And eventually, the completely obvious thing became obvious to me. I realized, oh, because I've got preservation and progress, I can do this. But you can see here, people don't say any system constructively proved with small step can evaluate, but just these special systems that have lots of extra code to do an evaluator, very efficient evaluator, so that's good. But you get one for free. Another example of this is, there's another textbook, Software Foundations, and a different proof assistant called Calc. Agda and Calc are both called proof assistants because they help you write out and check proofs. And again, they build in special code to normalize stuff. using programs that manipulate programs in Calc called tactics. Agda doesn't have tactics, so I couldn't do this. So I was bereft. What am I going to do? And eventually I realized, oh, it's just built in. You get this for free. So that's great news. I'll pause. Are there any questions about that?
Hi, so there is a question from the chat. Someone is asking if preservation is like an invariant of Agda or the system.
Right, so if you learn a little bit about proofs, you learn about invariants. And yes, thinking of preservation as saying the type is an invariant is perfectly fine. So that's a good analogy to make. Okay, so I'm going to take just 2 minutes to say about an application of this, and I'll pause for more questions. That means we'll go a little bit over 10 o'clock for 11 o'clock for questions. Is that okay?
Yeah, that's perfectly fine. No problem.
Okay, apologies for running over. So just very quickly, I want to tell you about, I mentioned I work for IOHK, that's a cryptocurrency firm. Their crypto platform is called Cardano. And we have a smart contract language for that. The smart contract language is called Plutus, and it's basically built on top of Haskell. It's a library for Haskell. So you would write your smart contracts in Haskell. Now, smart contracts sometimes manipulate money worth a lot. The most famous smart contract system is something called Ethereum. And Ethereum is well known for the fact that about every year or two, there will be an exploit announced where somebody has found a bug in a smart contract and used it to steal hundreds of millions of dollars worth of Ether, which is the cryptocurrency of Ethereum. So it's really important that your smart contract be right and that you can verify that it's right. Now, much as I love Haskell, the Haskell compiler is huge. Being able to be sure that everything in Haskell is correct and does exactly what you want, and there are no bugs that somebody could exploit, that's going to be difficult because Haskell is so large and it's growing rapidly. So to solve that problem, what we do and what some other smart contract systems do as well is we have the surface smart contract language, Plutus, which looks a lot like Haskell. So everybody familiar with Haskell should find it easy to program in Plutus. And then we compile that down to a low-level language, which is very, very simple, and which you can write a compiler for and be absolutely sure that compiler is correct. So in our case, the particular small language that we use is not one we designed, it's one already known in mathematics. So lambda calculus has been around since the 1930s. System F was discovered. So there's the team working on Plutus. Here's an amazing thing that comes out of propositions as types, right? Lambda calculus was discovered by Alonzo Church. Well, was it discovered or invented? Let's say invented. It was invented by Alonzo Church in 1932. But at exactly the same time, Gerhard Gentzen was inventing natural deduction. And then, much later, in the 1970s, William Howard points out that the rules for this, for simply typed lambda calculus, which was in 1940, and the rules for natural deduction, which were in 1935, are identical. They're the same rules. They're just written down slightly differently. It took, let's see, 1935 to 1969, I think was the proof. So about 35 years, 2 generations before somebody noticed, wait, if you look at this and this, they're the same thing. And at this point, I would say, no, natural deduction was not invented. Lambda calculus was not invented. They were discovered. And our evidence that they were discovered is that they were discovered twice independently. And then the same thing happened. So we've got what's called the polymorphically typed lambda calculus. That was invented by John Reynolds in 1974. But doing things with simplifying logic, Jean-Yves Girard came up with the exact same thing and called it System F. And again, these were done independently in 1972 and 1974. And it took a while before people realized, oh, wait, these are the same thing. So we want a programming language for our smart contract language to live on the blockchain. Something on the blockchain is forever. You never get to change it. How can we have a programming language that we're sure we won't need to change in the next 45 years? Answer, pick one that was discovered 45 years ago. So what we do is, here's Plutus Core. It fits in just one slide. There's a little bit more actually than what Girard and Reynolds did, because we need recursive types. So these two constructs and this one construct are for recursive types. So they're old, but not quite 45 years old. Right, we've been doing a lot with recursive types. In the talk I just showed you, these are the three constructs that capture that. So it's a very tiny language, and we've actually written out the whole definition in Agda using this intrinsic formulation. We've done the proof of preservation in progress. That gives us an evaluator for Plutus Core. We then have a faster one written in Haskell, and we test the Agda one against the Haskell one. So we generate random terms, evaluate them in both, and check that they both give us the same answer. We do any test programs we've got, we evaluate them in both and check that they give us the same answer. So Agda lets us prove properties, define System F precisely, prove properties of it, and then we can use those proofs to test against our Haskell implementation. Even better would be to derive a fast implementation in Agda. That's a harder problem that we've not done yet. We can write it out in Haskell and then show the two are equivalent. So I'll just stop there. If you want to know more about propositions as types, there's a video on Strange Loop about it. It's described thoroughly in the textbook. So there's a paper online in Communications of the ACM. There's a Strange Loop video, which you can find on YouTube by searching for propositions as types. The textbook is available online. You can get it here. It's on GitHub, which is great because people all the time are finding typos or other small problems in the book, and they just put in pull requests. So this is fantastic. I love publishing in GitHub because it means your readers can fix all the stupid typos that you've put in the book. So thank you, readers. And then finally, I wrote a paper about this, which I presented at a conference in Brazil, and I got a little Best Paper Award. So there I am in Salvador, in Brazil, holding up my Best Paper certificate. Salvador is a great place. And here is a testimonial from Twitter. I will end here. I just proved commutativity of multiplication in Agda and got way too much serotonin out of it. Programming language foundations in Agda is amazing. Check it out at plfa.github.io. So, and yeah, this is what's great about proof assistance. It's just like programming. It feels like a video game. You've got these sub goals, and every time you prove a sub goal, it's like blowing away a zombie. And they get into sub goals, which are smaller and smaller. Eventually, you've killed all the zombies, and your proof is done. And it lets you say QED. So I encourage you guys to learn about proof assistance, Coq, Agda, what have you. My textbook is available online. There are others available online. It's really cool stuff. Have fun learning about it. The fact that we get to learn new things and that they're all so amazing is the best thing in my life. I hope it's a good thing in your life as well. And I'll stop there. Thank you very much.
So, thank you very much, Philip, for your talk. There are a number of questions that have popped up that we've saved towards the end. So Jasper has been collecting them.
Hi. So a first question that was very popular was from Alexander Bernauer. As someone interested in learning more about these dependent types, do you have some guidance about whether to start with Agda, Idris, Kok, etc.?
Well, of course, I'm going to say start with Agda because then you can use my textbook. Idris is very nice, and there are a few textbooks for that. Kok is also nice. There's some things about it that I don't like. I prefer Agda, but there are textbooks for that as well. So any of those are great. You can look them over and decide which one you want, but I'm going to recommend Agda because then you can use my textbook, and I happen to like my textbook, but I may be prejudiced, so you might want to look at the other ones.
Thank you.
Could I ask a follow-up on that?
Sure.
So there are the other types of proof assistance that are not based on dependent types, like Isabelle, for example. So how would you compare these two approaches?
Isabelle is great. There's some fantastic things that have been done in Isabelle. There was a mathematician who proved the, I can't remember whose conjecture it was now, but it's about packing. It turns out what's the most space efficient way to make a pile of oranges? It's the way that you will see them piled up in the grocery store with one layer shifted over another layer. Proving that mathematically was so hard that when the guy proved it, it was a 100-page proof. And the mathematical journals, the referees looked at that and they said, this is so long, we're not sure that it's right. And the journal editors went back to him and said, well, we're not sure we can publish this because the referees aren't sure that it's right. And the guy went, what am I going to do? So he decided to use a proof assistant to write out the proof in full. And he hired people to help him turn that into a proof done in full with the proof assistant. He happened to use Isabelle. So Isabelle is great as well. Isabelle has lots of stuff in it that makes it easy to engineer proofs and to do them in a way that's easy to read. Kok, I think, is less easy to, it has stuff in it to help you do the proofs, these tactics that are programs that generate programs. So I've not said about tactics. Tactics can be important because you can come up with a set of tactics, and if you change the theorem just slightly, the same tactics still work. So they're very important in getting proofs that are not fragile, but are robust. So if you want to prove something really hard, like this conjecture I just mentioned, or like the 4-color problem, which was done in Kok by Georges Gontier, then you might want a system that has tactics. So that would be Kok or Isabelle. There are trade-offs between Kok and Isabelle. They're both very nice systems. I have some experience with Kok, less experience with Isabelle. Many people swear by both of them. Many people who have used them swear at both of them because it's a computer. So of course it's going to be frustrating sometimes. So there are different trade-offs between them. Isabelle doesn't have propositions as types in it, which I like. Kok does. But they're both very well engineered systems. Isabelle is possibly slightly more nicely engineered, is what I'm told, for doing readable proofs. So that's the trade-off between them. They're both worth looking at, I think. And there are new systems around like Lean, which also seems to be very well engineered. So if you wanted to look at Kok and Isabelle, might also be worth looking at Lean.
Great, thanks.
Another popular question from the chat was if you can you say that in Agda, a library is actually a collection of proofs that other people did so that you can reuse them yourself, so you don't have to prove everything yourself from scratch. Would that be a correct assessment?
That is absolutely correct. And that we saw the Agda standard library for a moment. That has lots and lots of proofs in it. That's exactly right. And indeed, for each of these proof assistants, people are doing this. And then you've got, oh, wait, there's a wonderful proof here in Isabelle, but I want to be able to use it in Agda or vice versa. So there's a large group of people thinking, wait, what should we be doing about portability of proofs between these systems? But that's just an idea in people's, a gleam in people's eyes, as it were, and hasn't manifested yet. I would guess 10 or 20 years from now, I'm hoping that you will see that we have large portable libraries of proofs done in this way.
Someone else mentioned that Emacs has special support for writing Agda, and was wondering what other options there are for writing Agda except for Emacs.
Right. So everybody is used these days to having an IDE, an interactive development environment that supports you in doing things. And the one that everybody uses for Agda is just built into Emacs. So many people now think of Emacs as very old-fashioned, and they'd like something with a more up-to-date IDE. That's not available right now for Agda, I'm afraid. Actually, all of the IDEs that are available are a bit klutzy. So for Coq, you would tend to also use Emacs or use something called Coq IDE, which is okay, but it's not as nice as the various professional IDEs like Eclipse or Microsoft's VS Code that are available. So IDEs is one place where we need to see some more maturity. For now, it's Emacs. I have to say I use Emacs all the time, and I find it fine. Other people's opinions may differ. And in fact, if I broke the screen on my laptop 6 months ago and got a new laptop. I haven't installed Agda on the new laptop yet, or else I would have shown you live Agda and Emacs, and you would have seen what it's like. It's great fun, right? You just type one button, and all of a sudden your screen, which was all black, goes into color, just like the textbook I showed you. And that moment where it goes into color is when you know, yay, my proof went through. And there's this adrenaline rush you get when that happens. So I think it's fun using Emacs, but other people's mileage may vary.
There was one, oh, sorry. There was one question on the clarifications list. If a proof is a program, does it make sense to test these programs?
Oh, very good question. So, right, Dijkstra is famous for saying that testing can reveal the presence of bugs, but not their absence. And to know that bugs are absent, you must do proof. And then there's the idea, okay, I've proved it. There's no point in testing it now. But in fact, for real programs, you need both, because the proof will be of a model of the program. You need the testing as well to make sure your model was the right model. But for something like associativity, it is the model. There's no separate program, right? There's the program that defines plus, but that's in our system. Everything's in the system. It's all simple and smooth. You do not need testing. There's no point in testing the proof of associativity. You have proved it. You can test it if you want. If you had some doubts, testing would be a good idea. So you can test it. But in a proof assistant, generally, proof is enough. You don't need testing. For real programs outside of a proof assistant, I think you need both. But within the proof assistant, I think that proof alone is enough. And that was a great question. Thank you.
Great. Thanks for your answer. So there's I think a follow-up question to that. So is it possible to extract Haskell programs from Agda, like extracting ML code from Coq, or do you have to rewrite Agda in Haskell?
Oh,
Slightly
that's
related.
a very good question. Yes, I should point that out. So as I said, you write your stuff in Agda, but indeed, there are tools that will extract Haskell from the Agda. There are also tools that will extract either OCaml or Haskell from Coq. So you write and prove it in the system, and then you get a real program that you can run. That one, because it's a complicated chain, when you've extracted the Haskell, I think there is some point in testing the Haskell as well as having done the proof.
Thanks.
We also have a question about smart contracts. It seems that in the past, when there has been sort of exploits in smart contracts and money has been stolen, it had more to do with really a fault in the logic of the contract itself and not really a fault in the compiler. So how does having dependent types help with finding logic errors in contracts rather than finding logic errors in the compiler itself?
That's a very good point. So you still want a very simple language that you can do proofs about and be sure that they're correct. So I think the method that we're following is right, but it's true. There have been, the problems have generally had to do with language design, things like overflow not being caught, or with the logic, things like having an invariant that you're trying to maintain, but updating the thing that maintains the invariant after a remote call rather than before a remote call. And then the remote call exploits that the invariant wasn't maintained. That's the DAO or DAO bug. So you're right. The problems are actually in the logic. And what you really want then is to be able to use your proof assistant to prove properties of your smart contract. So that's very important. And we don't know how you do it yet. As an example of this, right? How would you avoid the DAO bug? Well, there must be some property you'd want to prove of your contract. Which property is it? It's not entirely clear. So we're just at the beginning of doing this, but yes, doing proofs will be very important. There are some proof systems now, like Liquid Haskell, that let you prove certain properties of Haskell program. We should be able to apply those to Plutus. There's a new system that I just learned of a couple of weeks ago that also lets you use types to prove that your program runs in linear time. So you can tell how many resources you're using. Since when your smart contract runs, you have to pay for it. You want to know how expensive it is. It'd be nice if you could prove how long it took to run so you know exactly how much you would need to pay for it. So all of these are very important to do. We are looking at doing them. There's only very small baby steps available so far, but that's an important thing to do. Also, right, doing proofs is really expensive. So there are relatively few places where people are willing to do proofs. If you have a contract that's managing millions or hundreds of millions of dollars or pounds or what have you of currency, then yeah, you would be willing to invest in improving it. So this is a great area to be looking at, and we're just at the beginning of it. That was a very good question. Thank you.
I have one more question on my list. In Haskell, we have this tool called Hoogle that lets you find functions if you know the type. Is there something similar in Agda where you can easily find proofs?
Yes, it's exactly the same as Hoogle. So Hoogle, when it's finding a term of a type, it's exactly the same via propositions as types as finding the proof of a proposition. And yes, Agda does have simple proof search built in. So you're in Emacs and you type one key and it does a search. And if it's a simple proof, it will find it for you. It generally only finds very simple ones. It's not so good for finding more complicated ones, but for very simple ones, it can do it. This is actually a problem in the class that I teach because the students are supposed to be working out how to do it for themselves, and then they'll just type this key that gets the answer for them, and they've got the proof, but they don't know how it works because it was found for them automatically by Emacs. But yes, you can do that, and looking at ways of extending that, of making that process programmable so that it becomes more effective. This is more or less what tactics do, and Agda doesn't have tactics yet, but again, that's something that people are looking at, and I'm looking forward to seeing what comes up in that area. But if you need tactics, there are things like Caulk, which already, or Isabel, or I think Lean, which already have them. So if you need that, you might want to look at those other systems.
Thank you. So yeah, those were all the questions I had noted down. So thank you so much for your time and for also answering all the questions.
Okay. Thank you to everybody for your attention and for helping us begin to explore this brave new world that we're in.
Thank you very much, Philip. By the way, there are many clap emojis on the chat, so so that you see them as well.
Thank you.
Good. Thank you very much.
Okay, thanks very much to everybody.